Okay, so today we're going to talk about kalmen filterings, and we're going to introduce the process of the kalmen filtering iterations and explain what has been done in each phases, and give you a very good intuitive way of explaining why it has been done such way. Um, and also, if we have time, we'll give a detailed example of how it is being done. Okay, so before we dive into the actual process, we need to know what is Gaussian distributions. Um, in statistics, Gaussian distribution is widely used to estimate the random noise or systematic noise. So what actually it is? It is actually the bell-shaped curve such that the area under the Gaussian distribution will be equal to 1. And also, it has a mean, which you usually denoted as mu, and also another factor as the variance, usually as sigma. So you can see that the mu is where the curve has been picked. It is also the mean of this curve. And also the variance will be represented as how widely spread this curve is. So this very narrow one will have a very narrow sigma, will have a small sigma, while this very widespread curve will have even the same mu, same mean, but with much larger sigmas. So usually with very narrow variations, we can say that we have more confidence within this curve because the estimates are within very small range. While this very widespread one with large sigma, we can say that it's related to very high uncertainties. Okay, so that's a very brief introductions about the Gaussian distributions. So now let's have a really high level overview of what is actually kalmen filtering. So there are a couple phases involved in kalmen filtering. One is the measurement. So in each steps, we need to take measurements of the actual system state and do a evaluation based on the measurements. Maybe we can start from the predict phase. It's much easier from here. So what actually predicts do? So we have a system state at a particular point, and then use the system dynamic models. We can predict where it is, where it at the next state. For example, a car that is driving at a constant speed of 5 meters per hour will start at 0 meters, for example, and then after delta time equals, say, 5 seconds, where the car is now. As you have predicted, it's 5 times 5 equals 25 meters. That's where the car it is. That's exactly the prediction phase. So this example, we have used a very simple model, assuming the car has run at a very constant speed. So essentially, we use the system previous state as input to and then use the dynamic function of that particular system, which is a model that we can predict its next state. And then we have the output of the predictions, and this one will then go to the update phase. So what exactly happens in the update? So the update is that we take the measurements. For example, we have a radar here that measure the car distance at a different interval of times. Then we can use this measurement to improve our initial guess about the predictions. So that's exactly what has been done here during this phase. So using that measurement, we improved our beliefs, or we update our beliefs about the current state, and this will be the next state that going forward. And then using that current state, then we predict again the next state. And then again, it will iterate through the same phase, and it will go to the update, and then take another measurement, and based on another measurement, then we improve our predictions, and then as the estimate of the current state, and then we predict next, and so on and so on. Just one thing to be noted, that the initial state will be only used at once, because previously we do not have any data about the previous state during the iterative process. So we need to initialize the initial state of our beliefs about the current state of the system. For example, we can just eyeball how high the building is. It could be pretty rough about the initial estimates, but that's fine. Generally speaking, the more accurate about the initial estimation, the faster the kalmen filtering will converge to the true value. But if the estimate is is pretty rough, that's fine. So the initial value will be only go through once. So when we don't have the previous state and data, we go through the initial estimates and then go to the predictions, and then the same process, we go to the estimate, and then we do go to the initial state, and then we go through the predictions, and then update, prediction, update, and so on, and so on. So that's a pretty high-level overview of the process for kalmen filterings. Next, I'm going to explain what each step is doing and why it has been done such way to give you an intuitive view of kalmen filtering. So let's introduce some couple of terms here. So one thing that we need to talk about is measurement uncertainty. So what is that? Measurement uncertainty is something that is built in within the system. For example, if you measure the temperature of the water, so even the water temperature, say, is 5 Celsius degree, but your measurements at different time would be 7 Celsius, 5.5 Celsius, and so on and so on. So why is that? It is some systematic internal error that is within this measurement instrument. So usually we can acquire this one from the manufacturers, from the vendors. So it could be the constant value, or it could be dynamic. So what does that mean? For example, the radar. If we get the beam width and also other parameters, then we can calculate how confident the radar is about its measurement, about this time. So this is a measurement uncertainties. So generally speaking, it is about how uncertain the measurement instrument is, or how accurate the instrument is. Another uncertainty we call is estimate uncertainty. So what does that mean? That means that your actual value, for example, with your prediction. So here is our prediction according to the kalmen filtering, and the one highlighted in blue are the actual value of the system that we're trying to measure. So any gaps that in between with the prediction that we think and the actual value, we call it the estimate uncertainties. Okay, so I think now we can begin with the predict phase. So in the predict phase, we denote the estimates of the next state as x hat and n. What does it equal to? It equals to x hat n minus 1. That's the previous estimate, plus, for example, we are estimating the car distance from the origin driving at a constant speed, that would be delta time times its constant velocities. Okay? And its velocity that we assume that it won't change will be equal to the previous velocity, and n minus 1. Okay, so that's basically the predict phase. As we have discussed above, it will depend on the system dynamic. Usually we have a function to do the update. So generally speaking, it is just a model to model the object that we try to measure what the next state is going to be. So that's the predict phase. And we also have update phase. So what do we actually do here? So generally speaking, what we do here is that we, given the measurements and also the predict phase as input, we have measure, that way to produce a better estimate of the current state. So how do we achieve that? Concretely, it could be written as xn n hat will be equal to xn minus 1 plus k n x y1, sorry, in minus xn hat n minus 1. So what does that mean? Here, this is the previous estimate, and yn is the measure. For example, we take from the radar that send beams to the car to estimate the distance where the car is at right now. So the car is driving at that speed. So that's the measurement of the distance that the radar gets from the car. And what's that? The x. So that's the whole term that we call innovation. That's the difference between the measurement and the previous estimate. And here we can notice that we have a term called Kn. So what actually is that? It's called common gain. So Kn is usually between 0 and 1. So here we can see this common gain as the weight. So what does it mean? So we have our previous estimates, and then we have the measurements. We take the difference, and then we put a weight on such a difference, and then plus the original estimate to get a new estimate. So that means that based on the measurement, how much we trust about the measurement, so that we can do some adjustment to our initial estimates. We can do some tricks to actually modify this equation to a different format, which can be written as a result of some changing of the terms. It can be written as such, plus k and yn. That makes this even more interesting. So what does that mean? So we have 1 minus k and kn. And k is between 0 and 1. So that's actually a weighted average between these two terms. What are these? This is the previous estimate, and this is the measurement. So we're actually taking a weight for the previous estimate and also the new measurement. So intuitively, we should think that if we have a more accurate measurement, then the weight of the measurement would be higher. And if we have more confidence in the previous estimate, and then the weight of the previous estimate should be higher, so that we can have better results of the estimation. So that really achieve this kind of results for such weight. So we need to have a look at the actual implementation of the Kn, which is the common gain. So how actually common gain is computed? So common gain Kn is actually equal to Pn divided by Pn plus R and N. So what are these new terms? So here Pn is the estimate uncertainty that we have talked about before. Same thing here. And Rn is the measurement uncertainty that we have talked about before. So that's how we compute a common gain. This actually really makes sense. For example, if we have really high variance about the measurement uncertainty, that means Rn is really high relatively to Pn, and then we will have a very small value of the Kn. And then we have a small value about the Yn. That means that if we have a very high measurement uncertainty, then we give a very low weight to the measurement. Vice versa, if we have a very high uncertainty relatively to the measurement uncertainty, the estimate uncertainty is really high, then this turn, the common gain will be really high, and then we give more credit to the measurement because the previous estimate, we don't have very confidence in it. So that really makes sense for this term, the common gain. However, we do need to include the update in the and predict in the for the uncertainty part as well, so that we can include this part as well as the actual system estimate in the iterations. So here, in the predict phase, we can say that Pn would equal to Pn n minus 1. Assume that we do not have any changes for the uncertainty for the prediction. Again, all the terms here are determined by the system dynamic. Depend on different systems, we use different models, therefore all these functions are going to be different. And also in the update phase, Pn would equal to Pn n minus 1 times 1 minus Kn. Okay, so we can see that this is consistent with the equation here because we use the weight for the estimate. So the weight will be applied same here for the estimate uncertainty of this stage. So let's have a look at the overview of the predict and update phase. So firstly, we have to predict the next phase, the distance of the cars and the velocity of the cars, also uncertainty of the cars. And all of these will be as inputs for the update phase. How? The initial estimates x and n would be equal to such. But before we do that, we need to compute Kn. So how Kn is being computed? We need another input from the measurement, which is Rn. Because it depends on the instrument of the measurement, so the measurement can provide us that uncertainty on each round of measurements. As we can see that from the previous equation, this will be equal to Pn divided by Pn plus Rn. So now we have that one, then we plugging the Kn into these equations. Measurement also provide our Yn here, so that's why I can go to this equation here. to compute the estimate for now, taking into account of the measurement. So now we have almost a complete picture of the Kalman filterings. Just one more thing that we need to consider, which is the noise of the system. We didn't consider the noise in this example. Actually, what is noise? So, for example, if we have a water here, then we have a thermometer to measure the water temperature. Assume that the water temperature is constant. Does not change. Say it's 5 Celsius degrees. But actually, because of the external environment, the like atmosphere pressure or anything else, that would actually change the water, so that the water temperature actually would fluctuate a bit. So we can capture this kind of phenomenon into the prediction phase. So here we can add another term called Q, which represent the process noise. That's how we call it. So what actually process noise represent? It will represent anything that model cannot capture it, or any uncertainty that this model has. We can capture that. So we do need to include that one into this Kalman filtering in order for it to work. So now we have already go through each of the phase. So we have, let's summarize the Kalman filterings and go over again its iterations and have a really good intuition how it works. So firstly, initially we have a initial state. For example, we have the car at x0 is the initial space and initial place, and the v0 at a constant speed. That's really a good estimate. For example, you can eyeball the car where it is, and also you need to provide initial initial guess about its uncertainties estimation. So how confident you are, for example, about your estimations. And then it goes down to the prediction phase. So, for example, we need to use the velocity times time plus x to get the new locations of the cars, and also we need to estimate the uncertainty as well about the estimated uncertainty about this car, which is here. And then, since we have the updated, the predicted uncertainty and the predicted states, then we go up here to the update phase, where we will have an input of a measurements and also measurement values and measurement uncertainties. So using Rn and also the inputs, which is Pn, then we have Kn. And using Kn, then we can estimate the current state of the system. And also, using Kn and the Pn, we can update the current estimate uncertainty, which give two outputs. One output is the system current state estimate and the current system uncertainty estimate. And then the circle will iterate through again through each phase, going round and round, around and round, and it will the guess will getting better and better and better. So eventually, it will converge to the initial the actually true values. So one thing that needs to be noted that there could be gap in between the initial guess, the true values, and also your estimations. For example, this is your estimation, and the green one is the true value. This could happen when your model is not correct. For example, you assume the car is driving at a very constant speed, but actually is go really fast and then slow, and then really fast and really slow. In this case, the model didn't capture very well about what actually is going on. It will create a gap in between the estimate and the true values. In this case, we can increase the process noise. Sorry, it's Q. As we have previously discussed here, the Q values here. What does that actually mean? That means for this model, we assume that it's driving at a constant speed, but actually the system could go crazy and accelerate at a very different rate at a very different time. So we increased actually the process uncertainty of the system. By adding that, we are able to capture this uncertainty in the system, and the result will turn out to be much better than the initial estimate. But most of the cases, we would like to choose the model that is close to the reality model, so that we can capture, we can reduce the Q as much as possible to have a better estimation. So yeah, so pretty much that's the overview about kalmen filtering, and try to give you a good intuition of how it works.